how we really do it, not what ends up on a slide, then we can also talk about this. But let's start off at this point, right? I showed you the basic toolbox that we have available in cavity optomechanics. And I showed you some of the ideas that people had on, you know, creating entanglement or similar things. And what I would like to ask, and everyone can think, of course, for a few minutes, maybe you had an idea already. Now, with this toolbox, what would you like to do with it, right? And do you have an idea on how one would do it? Right? I mean, as an example, that is kind of taking away the most obvious. One of the goals, right, as far as I understand it, if one wanted to now have this macroscopic systems and do something meaningful in respect of, I don't know, coherence series, then one cannot just live with some Gaussian states. Right? So one needs to do something better. Yes, please. It's there. So in contrast to all these other photons, so I repeat the question, maybe not everybody heard it. That's of course also a good idea. If there's questions, I will of course answer. So in contrast to all of the useful photons that are taking part in the optomechanical interaction, there's some photons which would be absorbed. So in the end, an electronic excitation. And that would then really the whole, I mean, it's not this tiny h bar k which is doing something, but then the whole h bar omega is you know, pumping energy into the system. And that would heat up. At the first point, it would heat up at much higher frequency, but then this dissipates through the system. It just thermalizes at one point, and they showed actually in this experiment also how long it takes. I don't remember the number. At one point, the mechanical mode. Yes, that's a way to go, and not the last reason I think why the microwave capacitive experiments are so successful. I mean, there you don't face this problem, right? But for the other system, right, you can't just choose any material and try to do that, right? I mean, people have really cool ideas on all kinds of things on to avoid this. For example, just to mention one thing, there's an idea to use liquid helium as a mechanical resonator because you wouldn't have absorption in that. And there's actually two ways. One that is really being done is that one has a fiber cavity in a tube, so to say, and then one puts the liquid helium in that, and it's all covered by the helium, and then one looks at the compression modes of this. And the idea was that there's virtually no absorption of photons, and therefore the system wouldn't heat up, and that there's a super high mechanical quality in this mode. But what they are struggling with is that while there is no absorption in the helium, there is quite some absorption in the mirrors that they have. So the mirrors heat up, and by a second sound, that disturbs the helium. It's a very nice approach, and they have ideas how to actually get rid of this. I think now I'm struggling. I think it's Jack Harris group. No, it's a normal fiber. I don't know details about the experiment, but I believe it just comes in through the tube. I guess the liquid helium would go anywhere where there's a little surface just along the surface. So it just flows in. In the end, the system is in comparison to what I showed partially, where you have these bulky big mirrors. In the end, the system is a long fiber, and somewhere in the middle there's this tube where one has all the stuff, and one just needs to put this down into the cryostat. Any more questions or ideas? I think that was already a good start. We can find. I can still say the other thing that people try to do with helium is actually to levitate helium droplets. So you would take a few micrometer sized droplet of liquid helium, and that would be held by an optical tweezer. And then again, you wouldn't think of absorption because the helium doesn't absorb. You would also expect that in vacuum to be a very nice shaped thing, this droplet. And then the optomechanics that they want to do is to look at the whispering gallery modes. So you saw that maybe in the toroids that I showed. So when you have this surface, you can have a standing wave around the surface on a resonance, and that if the surface is very smooth, then this gives a very, very good ring resonator. And these ring resonators are extremely good cavities, but still limited a little bit by dirt on the surface or absorption or something. If with the liquid helium, one would expect to have, so say, the perfect surface. Right? I actually don't know how they want to couple light into that, because a cavity that is essentially closed is also hard to couple. But this is an experiment that is actually being set up. But in this case, there is, to my knowledge, no reference. And unfortunately, I also currently don't know the group. It could be Keith Schwab. I'm not sure. Oh, and then just to complete that, in Keith Schwab group, there's actually a microwave resonator where like a big one, right? Not like this little membrane one I had, but like a big one that is a cavity for microwaves, and that is filled with liquid helium. And there one wins a lot because, it's again the point, because there's then no heating effects, but then the coupling in this case, to my knowledge, is much worse, much smaller between the field and the mechanics. Yeah, or optimize one of the systems. As to my knowledge, the fiber people have some ideas on how to get rid of this. But I'm not sure I got the first part right. The light would then be guided in the photonic crystal, right? No. Yeah. I actually don't. If I got it right, I don't know the kind of system actually. Okay, I see. Well, I actually don't know, essentially don't know anything about that kind of system, so I can't really tell. I mean, we can think it through, right? So the light for the cavity, the light would be really then again in free spaces. Yeah. And what could be an like mechanical component there? Aha. And what size would this be? Okay, okay. Mm-hmm. Yeah, actually, I mean, yeah, that actually sounds like something one really can think of, right? Because the other nice thing in this, as far as I understand it, would be that the mode volume of such a cavity is really small. And the mode volume would be high. Well, but in what sense high? I would have imagined now that such a cavity has compared to our bulk cavities here with you know, a centimeter length, that this would be tiny, no? Okay, because this is an important point. It would actually help because this mode volume, as you saw, increases the coupling to the particle, right? So on a related note, not this idea. I don't know. I don't know of anyone who would have thought of this way of realizing it. Uh-huh. Yes, but I think nobody is thinking about using it in the context of optomechanics. Right? At least I would. Yeah. Yeah, I guess that wouldn't be a very clever way to do it with spraying. That's right. So as this discussion like kind of focused now into the middle very much, before we continue, I wanted to see first, is everyone hearing? I mean, you hear me, I'm pretty sure, but do you hear people talking in the front? And yeah, and if you think we should redirect or so, if you think, oh, now it's getting too far in the same direction, then just interfere. Okay, it should be like we want to like talk all together. But now on that note, yes, one would have to think of a way how to load in this, and in fact, similar problems are being faced by people today who want to couple the nanoparticles to some kind of photonic crystal structure, or actually there's these ideas to put the nanoparticles in like little traps that essentially are made of holes in the surface or so. In all of these cases, one would need to solve the problem of how to get the particle actually at this place. Now, it's maybe not possible in all of these cases, but there's my favorite way of transporting particles, which is based on hollow core fibers. If you like, I can show you something on that later on. Yeah, but then as soon as your structure allows for that, like people are moving this kind of tweezers around, right, and to position it. So I think there's ways to get it there. Yeah, actually, wherever we can do it in vacuum. Yeah. So yeah, That projective measurement. Yes. How to determine it, or so that's where this proposal is different from a grating, because no, it's not here anymore. So if we wanted to use the grating, somehow we would have to have a coherence that is, what you say, much bigger than this wave thing. But if we want to do this kind of projective measurement, then a particle, so that would be only displaced. No, if we have a wave function that is only very much smaller than, how do I draw that? I didn't draw it well, sorry. So if this is the standing wave, right, then and my particle would only have such a tiny distribution here, I have still some probability to measure it, for example, here. And I don't know if it's here or there. And then that would be my slit size. And that slit size can be much, much smaller than the wavelength. Because, yeah. Yes. 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 That could be that small, yes. Yeah. Exactly. But this is also at the same time the reason why one would always have a different slit size, like for each measurement. It's probabilistically different. I actually, yeah, so can be is always hard, right? I mean, I don't want to be one of the first. I probably will not be cited by future generations, so it's not so dangerous. But then you'd never want to be the one like Schrödinger, who said we will never be able to work with single atoms, and then everybody giving a talk about single atoms says, well, Schrödinger said that we can't do it, and still we can do it. But then on the other hand, in the first place, I would say it's very complex, right? So the degrees of freedom in anything that's living is so immensely high, and the teleportation would mean that you have a quantum correlation with involving all these degrees of freedom, right? We're super happy that we have the XP right now, right? Or a bit, or actually, like, meanwhile, many bits. But in that sense, yeah, I think it's very far future. Those generations won't remember me, or and on the other side, it's the question how much one would want that, right? Because you still, I mean, what you teleport is the whole information about the thing. But then on the other side, you do need the material that this information is written on. So in that sense, the teleportation implies that you want to bring something and then teleport it, right? You don't want to know in advance, okay, in the future, after my experiment is done, I will have this now there, because then you can also carry it. But so in that sense, you would have to provide a lot of material that you can write. It doesn't seem like a... but then I would also like to say something, because it's kind of fun. on the thing that I thought the question was going to in the very first place, maybe it comes from this. Because the first proposal one of the first proposals on this levitated nanoparticles was actually in a very courageous title by Oriol named creating quantum superposition states, something like that, of living objects. So the question there, of course, that was all calculated for the nanoparticles and so on. But then, of course, sometimes when you have a beer in the evening, right, you can think of, well, would we actually, instead of using a nanoparticle, now be able to use some living object, right? What prevents us from using, well, something on the edge of what we call living, a virus? Right? And then this kind of question leads to new insights. I met someone who has been working on is doing biology essentially. At the time I met him, he was working with fungi, but before that he was in some group where they look at this. What do you call it? It's kind of strange extra. Yeah, these organisms which can live in geysers and in like all kinds of hot or so places, which have found certain strategies to survive at higher temperature, and then these people also look in whether it's actually possible that such viruses or DNA in some way can travel on meteorites, such that one can kind of sustain this theory that life on Earth came because some DNA flew with some meteorite on Earth. So the people have been looking at all these kinds of things, and I mean, levitating a virus that you could afterwards have reproduce again is not something that sounds totally crazy, because that typically doesn't absorb so much at certain wavelengths, so you wouldn't necessarily kill it. It can get reasonably hot, not as hot as our nanoparticles, which are probably far too hot. They can survive pretty good vacuum. That's what they found out when they studied for this meteorite stuff, right? So if one really wanted to go there, well, you could think of levitating a virus, and then I believe that the main issue we will have with our nanoparticles is probably stuff like absorption or so. So that would clearly be something that gives absorption if you use a biological object. So I don't see how you would make the superposition, but it's, yeah. The question, why would one want this? Right? Apart from that, it's just so cool, but if you had it, but then does it mean anything? Right? If one really looks, I've been asking myself this question, and if one really looks hard into the literature, then one finds some studies by NASA who were levitating, I think, 100 micrometer spheres optically. And if you want to go much larger in mass, then you need incredible laser powers. So that optical levitation, when you just do it the way that I showed you, with this nice picture from Arthur Ashkin, where you have this particle and the laser comes from the bottom, you wouldn't be able to come close to millimeters with any reasonable power from just the laser. But then, at the same time, there is this extremely this beautiful proposal by the group of Pinkoy Lam, where they actually, yes, and where they actually want to levitate really a mirror. And this is not just a proposal; they are really working on this. So it's a tiny mirror like these other mirrors, and it would be like on the order of size of millimeters, so much too heavy for what I just said. But their idea is to come with a kind of a tripod of optical cavities. You have like 3 cavities and the light fields, which would be reflected back into the cavity from this one levitated mirror. Right? When I was first told about this, I thought, oh, this must be a very, very, very ambitious PhD student who is starting on this project. But recently he's been talking about it at a conference, and they are really working on this, and they are putting a lot of money and effort in it. I mean, when you think about it, right? How do you get it there in the first place? Right? You have these. I mean, if you ever lined a cavity, this is already, if you haven't done it before, it's already not a nice thing to do. What this thing should do is that you have 3 cavities aligned at the same time by a mirror that you can then just leave alone, and it stays. So he showed some data on how they studied what would be fixed points where this thing would be lying, and of course you have a huge amount of power due to this cavity, intracavity power. And yeah, after one heard him talk about it, it looks really doable, even though it's really a tremendously difficult experiment. I think we can look forward to seeing that, and then that would be the largest object levitated. The shape of the particle matters for the polarizability. It goes into, so this equation which I wrote about the polarizability is just round particles. So it does matter. A tube would have a higher polarizability along the axis of the tube instead of orthogonal to it. When it comes to a carbon nanotube, I don't have any numbers on this, so I'm just guessing a little bit there. But my guess would be that there probably the polarizability is not so terribly high, right? Because it's still a very, very small object, and one doesn't have a resonance to talk to. So except there's something electronic one can excite along the tube. So I don't know. I would actually doubt it that it levitates before it burns or so. But okay. So it would, but as soon as it's levitated, there's nothing the heat can transport. Right? So sorry. Yeah, there's nothing. Yeah. So it shouldn't absorb in the first place. There were more hands just before. Yes, please. Very cool. Okay. Yeah, I didn't think about it. That might, once we have a superposition, that might increase the sexiness level of a publication by far. That's actually a very interesting thing to look at then. Yes. So it was something we can do. We had that, but we didn't do any studies on that. But yeah, there's actually different ideas. So if one gets the parameters right, there's certain proposals that a cooling of a joint mode could actually entangle the motion of the particles. And then there is, if one doesn't use a cavity but just a trap, the group of Helmut Rich looked at this, then the scattering between, like forth and back scattering between these particles would lead to a kind of self-synchronization in the distances between. So that's actually a really nice effect. It's something I really want to study. One system where this would be nice, but rather with disks than with particles, is also in this kind of hollow core fiber, because there one has a very confined mode, and if one could stack them in there, it's like, almost like a cavity. Is it what? That's right. Yeah. At the moment, this is exactly true. What we do, we get the particles kind of randomly into the lab. Now, this is one of the reasons why we wanted to go to this hollow core fiber approach, because then you can randomly trap on one side, but then you can position it when it comes out on the other. So another comment on the many particles actually. So because this is really some direction that I want to go to now. Just this little. It's for fun and it's not levitated. It's just if it works this time before it worked before. So I was told, so when one now thinks not so much in terms of the quantum physics, but more in terms of the thermodynamics of things, I was told by my theorist friends who are looking into that as well, that one could look at like heat transport properties of a chain of nanoparticles as well, because you can kind of get an interaction. In the cavity, it would even be tunable, right? In the or you just get it via the slide scattering, and then one can locally cool or heat the motion of one of these particles and look at heat properties. So also from this perspective, I think it's, I mean, there's a rich playground, and now it works. Huh? This is something I always like to show. If it works, oh, it doesn't work. Oh, come on. Sorry. So, so this is in liquid. This is in liquid, and it's actually a Tetris game. I don't even have the link here. People can, in liquid, manipulate like a huge amount of particles just with a single tweezer, because they can create complex optical potentials and then move all these particles around. And this is something that people have been starting to do with atoms as well. And so we know in principle that in optical levitation one can have many particles in like a complex optical trap and still manipulate that. Now at this point, I think there's only like double wells or so that people try to implement with the nanoparticles. I just look for this reference. Very good. Here you go. Okay, so not that I want to play Tetris with a levitated system, but I think that if one could do such a complex structure of more than one particle inside an optical cavity coupled via the same light field, then this would kind of be really also a nice system to play with. Yeah, so in the end, when the thing is over, then they just switch the tweezer off and they would just. Yeah, we have a long way to go until we can do this in a levitated. Now, as everyone's looking, and now I don't dare to switch it off anymore. I think it's not so long. I can have it running. I hope it's not repeating. Yeah. So while this is running, yeah, now they disappeared. Huh? Yeah. So I mean, I'm talking because of this project to create this kind of complex structures. I'm just starting this. I'm talking to people from like a biophysics department in Innsbruck who have been working on this for a long time. And when you visit them, right, then you can take the touchpad and say, look at these particles that they have trapped and just move them around with your finger. It's beautiful. And yes, they are going to kind of help me to set this up. For trapping, no cooling is necessary. The trap depth that we have is, well, it depends. In the hollow core fiber, we went to trap depths that are up to like 800 times the room temperature. So in the typical like tweezer experiments I've been talking about, it would be, I think, on the order of 30 or 40 times room temperature, but still deep. Yeah. In the same potential? I guess sometimes we do that by accident, but then we wouldn't really see it. We don't have a resolution of our optics for that. If one had a good detection, one would maybe see it in the optical signal for the readout. But again, when one comes with the tweezer or with the hollow core fiber or so, and one would really be able to do this handing over, that's on a much sub-wavelength scale, the positioning precision. So it would actually be possible. They would probably very quickly stick together if they're not charged. I mean, this is something when they come close to a surface or close to each other, if it's not in the water where we have it, they would typically just, van der Waals. Sorry? Yeah, they would have to be much larger, yes. Yeah. So, anything else? Otherwise, I mean, yeah. This is okay. So problem of quantum gravity specifically. I don't really know. I mean, yeah. Well, there is this kind of matter wave interferometry approach, right? There is, I mean, there's a general idea, and I can say a few words about that. This is again not based on my own thinking, but this is really speaking about where Markus Aspelmeier is planning to go to. If we want to make a meaningful experiment that includes quantum superpositions and gravity, in the sense that gravity would actually not be just a background, right? You can measure gravity and with these atomic fountains and so on. But if you really would like to do something like, likely you heard about this at some point, but if you really would like to do something like, I make a particle in a superposition state, right? I somehow show this like this. This would be a superposition of the same particle in two places. And then I have another particle here. And then the gravitational interaction might be the cause for the particles to get entangled, because if the particle was up there, it would pull the one here, and if the particle was down there, it would pull it there. And if you didn't have this in a superposition state in the beginning, it would just have to separate due to the gravitational attraction to these two spheres. So this would be kind of the thing you want to do, right? It's gravity causing entanglement. That I would call it quantum gravity or something. Yes? Sorry? Yeah. If there's no interaction, then this will not happen. That's what I'm saying. If there's no interaction between them, right? Then this particle would just stay where it is, and this particle would, they would evolve independently, right? They only start to evolve together when there's an interaction. If one can do the experiment such that the only interaction that there is gravity, which is really hard because there's all these other very strong forces. That's only one reason why it's hard. Then you would have gravity start to entangle the position of this object with that object. Now, I probably don't have to say that this is far from today's possibilities, because we talked about the higher masses in the optomechanics, but then these are very, very slow masses when it comes to wanting to see a gravitational interaction with something else, right? And we're already having trouble to make superposition state of those. Now here we would have the requirement to not only make the superposition state with the mass, but also have it so large that we can see the gravitational interaction. But one needs to start somewhere, right? And this is why we, in addition to all the very quantum-directed experiments, there's also one experiment that is just wants to use small spheres to detect the gravity of another small sphere, right? The gravitational interaction. So the idea would be, can we use a optomechanical object with like some big sphere here or so, and I take another sphere here, I move this sphere around, and I can detect the motion of this sphere via gravitational interaction on this cantilever. That's the problem of force measurement in the end, right? And this is something that's being set up with a size of millimeter big particles, and that would be sitting on a very complicated stage and would be moved around, right? And then this is in the current ideas, this is a sphere on top of one of the silicon nitride membranes, and one would optically try to read that out. So, and that's already independent of all the quantum. That's already kind of an interesting experiment because it's a completely different approach to measuring the gravitational constant. In all the estimates so far, for the first version of the setup, which is kind of planned now but not been set up, one would not beat the Cavendish experiments that have been done so far, but it's still meaningful because, as you pointed out this morning, it's almost always the same type of measurement that one wants to do if one wants to measure a big G. So a measurement that happens on a completely different length scale and in a different way would actually be meaningful because big G is the worst measured constant in nature. But then, yeah, here we're talking about millimeter-sized spheres. For the superposition states, we're currently talking about 10 nanometer-sized spheres, so there's still a bit of a gap. But yeah, so that's my kind of long answer to that. Sorry? Yeah. 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 To shield, yeah. Yeah. Yeah, no, we don't. But would you think of needing that in the context? No. Yeah. We can. Okay. Yeah. Good point. Yeah. If we set ourselves in a reference frame that is free falling, then we are shielded from gravity in a certain sense. Sorry. Well, that's essentially that idea, right? If you're in free fall, there's no gravity. How they provide it here? I mean, there's the like the flights, right? There's these 0G flights, but on Earth. Yeah, I don't know. Is it? Okay. Okay. You rescue. Yes. Mm-hmm. I did not interfere. That's actually a good point. They were thinking of shielding this in a way to avoid systematic errors. I don't know if that is in the final design, but you would have a membrane for shielding here that is just avoiding that effects between the two would start to play a role. But of course, one gets an interaction with this, but with this membrane, but it's static. And concerning the readout, if I understood your thought correctly, then you suggest a electric readout via the piezo instead of the optical readout. Well, first we're experts on optical readout, and and this is one good reason to do it optically. But then also I think that optical readout would I mean is really, I don't know if one can so generally speak, but is among the best position detections that one has, right? without concerning noise. But I mean, in the end, I do agree. In the end, one really has to calculate it to know what is the better way to do it. Would you have an intuition why it's? I see. Well, when it comes to noise, then there would still be a bit of a difference, no, between the magnetic solution and the yeah. But actually, the magnetic way would be also a very nice way to do it. No? If one of the particles was magnetic. Yeah, yeah, yeah. And then a squid to read it out would be an option. Yeah. So I without having a quantitative argument, my problem, so to say, with the piezos in my intuition is that you would have it mounted on something very stiff. So you want to detect this extremely weak force, and then you take this extremely high spring constant for your detection system. So I guess you can better judge that than me, but I would guess that this is the wrong approach. If I want to detect you had it on your slide even today, right? If I want to detect forces, then I better take the soft system, right? And if I want to detect position, I take the strong spring constant. No? Yeah. Okay. So in that sense, what was something soft like magnetic, yes, would be nice. So as we've been somehow coming, I didn't say that because of that, but as we've been coming somehow in this direction of magnetic, Hendrik was talking today about this nice skate park proposal by Oriol, and this is experimentally people haven't been doing much in this direction, but then of course magnetic levitation already for itself is something that is interesting, because if you think of what I talked concerning recoil heating of the levitated nanoparticles, magnetic levitation would actually not have that. So actually we're in Vienna, there's also one experiment being set up now on optical levitation. It starts off with like trying to levitate microparticles over some kind of Helmholtz coil system. But then, and this is why I thought about it now, then this goes exactly in the direction of what we've been talking now, because the idea of this in the middle term would be that this is levitated over a chip, and that one uses a squid to read out the motion of this sphere. And then we are almost already in this situation, right? Then one has this already now order of 10 micron sphere, which would be easy to read out and levitate it, and that could then be coupled to something else close nearby that could move. However, one would then shield the magnetic. So anyone who is curious actually about this, it's been worked out technically in much detail by Jonas Schmöhle, also in the Astelmeier group, and there's a paper on the archive sometime this year about this experimental setup. And the thesis will be seen. Any more thoughts? So if not, then we have several options. Right? But if you still come up with something, just stop me. Right? We have several options. There's half an hour to go. We can, I can still show you something. I can give you a choice of a selection of topics. That's one option. Or I mean, you don't have to fill the full time. So if I make the suggestions now and everyone agrees on not saying something that he wants to see, then it's also fine. Then we just close the session. Which doesn't mean that I don't want to show it. Right? But so as I said, I will talk mainly about all the optical levitation things, some of which you saw already on Monday, which is one of the reasons why I didn't have this in the talk so far. But what I do have is I have slides. In case you, for example, are here on Monday, I have a few slides on transport in hollow core fibers and what we did with that. I have a few slides, but this is then not my work. I just brought them on the first steps, baby steps towards magnetic levitation. I mean, it's more or less a way to show how hard it is to get this kind of thing running in the first place. And I can also still give a few comments on like my first steps towards trying to do stochastic thermodynamics with levitated particles, which is essentially a study of just a theoretical proposal at this stage, a study of a stochastic heat engine, which is based on a levitated nanoparticle, and therefore very much out of the topic of this conference. So anything he would really like to see? Okay, so that's already, I mean, that will probably fill the half an hour if I show the two, and if someone wants to see the thermodynamics, you can still come to me if we did. Okay, so everything. So we need to make votes. I'm very happy that you said that you want to still see something. Okay. So let me think. I was considering whether we should make a majority vote right now, but I actually think that maybe because it's my kind of out of my team, and it's also something that came up several times by now. Maybe I just say a few words first about the hollow core fiber, and then we see how far we come. So this is kind of an artistic image of what we thought we want to do. Here you see optical cavity, and then a hollow core fiber would come here, and we would like to move the particle out here. The whole cavity could be in high vacuum, while the other end of the fiber would be at room temperature. You can gap like 10 to the 9, or like you can get like 9 orders of magnitude of pressure, I think, with a 10 centimeter fiber. So this is, we can transport it over much longer distances. So this was the original idea. Now, we're currently using the tweezer, which shows you that it didn't work the way we wanted when we connected to the cavity. But yeah, so here you see some things we did with the hollow core fiber. So this is not the first time people put nanoparticles or microparticles into hollow core fibers. So the group of Philip Russell, which is in Erlangen, have done some conveyor belts, some sensing system, and similar things with this. So this is a hollow core photonic crystal fiber. The light inside the fiber is guided, despite of the fact that the refractive index inside is smaller than around, because of the photonic crystal, which confines the light in here. So one gets a nice mode, a nice fiber mode. The size of this is for a 1064 nanometer laser, roughly 10 micrometer of this hole, which would give pretty much a single mode fiber. And then the idea was, okay, let's take our funny nebulizer, go into the chamber, and have a standing wave with lasers coming from both sides, trap the particle here, and then detune one of the two lasers, which gives you a moving wave, which you might know from atom experiments like in the Mesoscopic group, and then this particle would like travel through here. If you're not asking me about it, then I probably won't go better through the whole setup, just the main points. We have AOMs on both light fields that go into the cavity for such that we can make the moving wave. And we can look in transmission of one direction, we split off some of the beam. This is actually an old version of the setup, and then go on to some position readout. Now, the position readout is in the first place very simple, because the particle scatters some light and it moves, and the motion of the particle with respect to the standing wave gives a phase shift that is position dependent, and the interference between the traveling wave and the scattered light is something one can directly see as an intensity modulation that is position dependent. So we just need a monitor. As it you will see that in a moment. So this is how it looks like if you take a PlayStation camera and point it at the system while the particle is moving through. This is roughly in 15 centimeters here. We can we can set the detuning of the two lasers in steps of 10 kilohertz, and if one switches this on, then the particle moves here with, I don't know, a few centimeters per second through the fiber. That is something that has, this movie has been taken at a relatively high pressure. So that's like a few millibar. Because I mentioned this before, that there's this kind of particle loss, and this loss of particles also happens in the hollow core fiber, and so far we don't have a way how to get to really low pressures inside the fiber. Now one can characterize the whole thing a little bit, and here, if one moves a particle step by step along the fiber, we can position it quite nicely in here. Then one sees a modulation here of the trap frequency with position, and this is when we found out that this is not truly a single mode fiber. So one can explain this modulation by taking into account that first, the corresponding thing in a fiber of a TM01 mode would be traveling along with it, and then the two modes together, they have a slightly different K vector because they have they enter the fiber a little bit differently. So this slightly different K vector gives rise to a modulation on the order of hundreds of micrometer in the interference between these two modes. And this is why the particle would sometimes be trapped here and sometimes here, and one gets this modulation of the frequency, which is a nice calibration of the position where the particle is. And then we can move the particle out of the fiber. And because this is a Gaussian beam, it would expand out of the fiber. The mode field diameter is 3 micrometer, so it strongly expands. And this expansion makes the trap wider and therefore reduces the frequency in the trap, which is why here the frequency of the particle drops, and one would have to increase the intensity of the laser in order to keep the particle trapped. The important thing is that we can move it out far enough such that we don't disturb the cavity mode with the fiber, right? If we want to do the transfer to the cavity, then the fiber cannot stack into the cavity mode, otherwise the finesse of the cavity is just killed. So now what we did further is we wanted to keep this particle even at low pressure, so we added feedback cooling at the first place in one direction. There's a green laser coming in here. It's a green colored line here, but the laser is actually red, sorry. That can be intensity modulated. We have the readout along this position, and we can do feedback cooling. So whenever the particle moves towards the beam, we make it strong, and whenever it moves away, we make it weak, and that cools the motion of the particle. And here you can see out of a set of, I don't know, I think 10,000 traces, where one actually switches the feedback cooling on, leaves it on for a while, and then switches this off again. One can monitor the energy of the particle, calculated via equipartition from the position out of this ensemble of 10,000 trajectories. And what it gives us, this is kind of a ring down to a cold temperature, and then here it would heat up again, and this peak here and this feature here is just from our detection. When we do the switching, we get a stupid signal. So that's not a tremendously good feedback cooling. It's 5 Kelvin, and the reason for that is that if you use a high NA objective to read the position of the particle, then you can really give a very good feedback. But here we just have the NA of the fiber, and that is much smaller, and therefore our position readout is limited. We can go to lower pressures when this feedback is on sometimes, but it seems like we need an additional feedback radially. That seems feasible because due to these higher order modes in the cavity, one can actually also read out the radial motion. This is the red lines here. And we really have a 3D monitoring of the motion of the particle in the hollow core. Now one question always came up. Yes? What we do is essentially a D, yes, and actually we need to do PD. In that sense, it's completely right. We cannot cool there is also still some noise inside, but in principle, if one cannot cool with this controller colder, then you can resolve the position, right? Because your signal is just noisy from that point on, and the thing you act with is not the particle. So in that sense, I think I don't know how well David optimized it actually, but I think that this is kind of the parameters are optimized, and we're limited really by the detection. Yeah, this is what I want to say. Now, one question always came up as we want to go to this low pressure, right? There was this question, how is actually the pressure distribution inside such a fiber, right? If you go to a very low pressure on this side, and a high pressure on this side, how is the pressure distributed along here? And then you look into the literature, and then you find out that it's actually not that clear. I mean, there's even contradictions in the paper. Now this can confuse one a lot. In the end, we did a measurement, and this measurement showed something that one would have to expect in the first place, namely that there's a linear distribution. That measurement was done when the loading chamber was at a few millibar, and the science chamber was in very, very, like a 10 to the minus 4 or so. And why I say one would have to expect the linear dependence is that this is not more than a kind of diffusion process. So any of the gas particles would hit the wall, stick there, randomly go off the wall again in a random direction, stick there, and then you essentially see a diffusion of the particles through the fiber, and because the gas pressure is so low already, this is for each particle individually the same, and then this is a linear drop pressure. Most of the papers, and this is where the gap came from, looked at a bit higher pressures. But it turns out that measurements hardly existed because it's not so easy to measure the pressure inside a capillary of 10 micrometer size. So we actually learned that this is the nanoparticle is a nice tool that this community, which we didn't know about before, actually needs. So we have this measurement of the damping. So this is the damping of the oscillator, the nanoparticle oscillator, versus the pressure, and we see this linear dependence that I was talking about already. And this can calibrate our nanoparticle pressure sensor, if you like. And then if we move the particle along the fiber with this gap, this is a log scale, so don't get confused by that. It looks nicely linear here. It actually stays linear. It's just that this whole curve has an offset, and that is plotted on a log scale, and this is why it looks so curved here. So we need to do two types of measurement in order to determine the line width, because at very high pressures, the feedback cooling doesn't work, but we can have a nice line width measurement by looking at the width in the spectrum, something that we saw before. When we go to very low pressures, then due to a drift in the intensity of our trapping laser, actually this Lorentzian peak would be shifted around, and we see some kind of inhomogeneous broadening of this. Right? When the peak moves and has a width, we cannot determine the width from the peak anymore if we measure for too long. So this is why this measurement with the relaxation here is used for the red data points. One just looks at the time scale for thermalization of the system. And this gives us also a value for the damping. So this gives us the whole pressure distribution all along the fiber. And then we got in touch with Tonseda, who was very interested in doing simulations to compare what we measure with what they simulate for such a system. And they do the full gas dynamics along the fiber. And this data is not at the end of the simulation. That's why it kind of has a big error still here and stops around here. Because this simulation, when we got it, it's already a while ago, was already running for a week. So it's something that is really difficult to simulate. And they found that this agrees, and this is in contrast to some of the work on this, but it's also not the end of the story, because as it turns out, we are in this regime where the particles can be treated individually, and of course for higher pressure this is not true anymore. So when we go to higher pressures, and this is something that I don't yet have on slides, when we go to higher pressures, then this dependence becomes nonlinear. And this nonlinearity is something that we can see, but we couldn't resolve with our pressure measurement devices so well. So we had to improve the setup. David has done that already, and we're now looking at this nonlinear cases. This is to say that out of our whole goal of doing quantum superposition states, we ended up now doing some work for gas flow, rarefied gas flow in capillaries. Quite different, but it's fun. Yes, so that was essentially what we have on the whole. We are coupling a Gaussian beam into the fiber, and in the fiber, because of the boundary conditions, it's some kind of LP mode. Yes. No, what we use here is having an intensity maximum at the center. It's not exactly a Gaussian beam, but it's essentially a Gaussian beam. One can only trap the particle in the, so that would be one of the higher order modes. And one can trap the particle there as well, because it would still be far away from the surface of the fiber. And then it would be on a ring. Actually, the Russell group has done some kind of experiment where they look at the two modes together and then they are moving together. But there's more work on this, where one traps the particle actually in the center of the donut-shaped beam. But that doesn't rely on radiation pressure, but that relies on photothermal forces. So there the trick is that the particle would be kept there because of the surrounding air. Yes, that's right. We actually can do that too by going far away. Trapping in the. It's not so easy to. I mean, here we just you just align to the Gaussian beam to the center. If you want to do the other thing, I think the Russell group used SLM, so a spatial light modulator, to get the donut-shaped beam nicely coupled. Local fiber, but no, there's no. You have an idea of what one would do with that, or just out of fun? Okay. Ah, okay. That's nice, because actually we had some polarization issues in there. We didn't know what happened to our polarization. It seemed to just get crappy instead of being conserved or rotated. Should we? So we could make. So who still wants to see? I mean, if you feel like that you had enough, also to Steve, I don't feel offended. but yeah, otherwise we can make a quick quote. You want to see something on the stochastic thermodynamics or on the magnets? The first version, stochastic, magnetic. You're really good at this. Now I don't know what to do. Okay. I suggest I just show you a few slides on the magnetic thing, and for those who are interested, we just sit together either today or tomorrow after the lectures, and I tell you a bit about it, because then we can discuss it also a bit for everyone. it's also I will also get into talking when it comes to that subject. And time's also running out. Wait, just a second. Sorry for that. So the magnetic levitation is really something that has been started very, very recently in the group, and these are the main actors on the Vienna side. There's a lot of collaboration. This is Joachim Hofer and Joshua Slater and Witlef Wieczorek, who is actually now going to do similar things in Kaiserslautern soon. And I won't go much into the details. So the idea is, as I said, that you neither have clamping losses as you have with clamped systems, nor you have photon scattering. And then the whole thing is already very cold, which is nice when it comes to comparisons with respect to blackbody radiation. And then people would expect to go to a mechanical Q beyond 10 to the 10. And there's many collaborators on this coming from like one needs to build squids for the readout. There's a lot of theory support. Then there's the idea of this chip-based trap. So this is all being done. And one of the first things that they did was essentially have the workshop create such different versions of such holders with anti-Helmholtz coils. And then this up here is a movie that is actually running. So very slowly this particle will levitate. And they have a single IFCO particle, so that's a type 2 superconductor. And this is at the moment really mainly to play around because it doesn't have the really low temperatures yet. Of course, later on you would really see it moves a little bit. This is when ramping up the field. So this is mainly for playing around, and you would like to have type 1 superconductors at the later stage. So this is a single and a few micron sized particle, and one has enough time, then one can actually see that you can see it already that it levitates. So the way this movie is taken is it's shining in via a mirror. So this is inside the cryostat, right? So there's a little two little space, and one is shining in here from looking via a mirror here from the side. And what you see here is essentially the floor of this little podest, which you can hardly see. It's a little podest sitting in here. And on top here is actually a holder that would later carry the squid. And what is going on is that they have had a micro squid used, but then the problem is that you cannot have the squid easily operating at very high fields, but it needs to be very close to the very high field gradients, but it needs to be very close to the particle. So the micro squid actually died when tried to find the zero field gradient there. So they are already getting nanosquids, which would then be moved with some translation stage in here and would be used to read out the particle. And the other thing that is going on is the design of a chip-based trap, which would be more convenient for many reasons in comparison to this anti-Helmholtz coils. And there a lot of work goes into actually getting the thing operate with very high currents inside the pipes. So this is Josh, and he actually was meant to go for a few weeks to Munich because at the Walter Meissner Institute they know everything about cryostats, and we wanted to learn everything we need to know about cryostats. This is while he is actually, in order to characterize the squid, he's sticking it into the helium, the liquid helium. And oh, this is already all. So this is essentially where the project is right now. So it's going on for a year or so. They will be soon getting a new cryostat. What means a new cryostat? We have one already, and they will be getting their own one for the magnetic levitation. And so that will be a dilution fridge going down to millikelvin temperatures, while currently they have to work with 4 Kelvin cryostats. And as you can see, the project has many aspects where one needs to do development, right? One needs to have a cryostat where one can work with this, operate with all these high currents. One needs to find a way how to get proper particles, like nice mechanical resonator particles that one you saw before looked slightly ugly compared to what we, for example, levitate. Levitation works. People are working on every aspect, right? The chip-based trap is being built by Trupke in Vienna, actually Josh could in his time there already show that he can attach the really strong current wires. Yeah, so this is essentially what I can say about it. The data is, so far we don't know what the frequency of the particle would be, because well, one could think of an optical readout for the whole thing, but then they really want to wait for the squid, and as the microsquid didn't work, needs to wait for the nanosquid, which is currently mainly waiting for the new lab to be installed for the whole system, because every effort after half a year, not a few weeks, is now redirected to Munich. It also, and that's the last thing, it also, there's this whole collaboration just got a European grant, so the whole thing is taking up momentum now. But as you can imagine, this is why, right, when one sees this kind of decoherence test with levitating small particles, I told Oriol once that after his talk, he's very passionate when he presents these things, that I would actually currently feel like I just switched to magnetic levitation, because optical levitation is sometimes going on my nerve. But then, yeah, this is, when you look at this, this is really at a stage where you cannot yet judge how feasible it is, right? We started off with the optical levitation in 2010. With Markus Aspelmeier at the time said by Christmas we will have the first results on that. Well, I was not believing in it, but yeah, it will still take a lot of time until we see that, and before the measurements don't show that technically this is a feasible route, I think one just needs to follow all roads possible towards the other options also, showing superpositions and matter wave interferometry and so on, or even in space. Good. Thanks. That was that. And yeah, thank you for being here so long.